Thank you. Welcome back to another video, and I'm going to go over the Math 111 exam number 2 review for the October 25th, 2017 version. All right, so it's only 8 questions. It's not as bad, but I'm going to go over it and hopefully see like different ways in which you can do each question. Now, for question 1, we have that, okay, we're going to consider the curve y equals, okay, 4 over x plus x over 2. And then for part A, we want to find the tangent line, right? So we want to find the tangent to the point 4, 3. For part B, we want to find the normal line. So we want to find the line that's perpendicular to the tangent line at the point 4, 3. And for part C, we're asked to find all points, okay? All points where the derivative, where dy over dx is equal to 0. So we want to find whatever, all points where the tangent line to the curve is horizontal. So first we take the derivative of this, right? So dy over dx over here is going to be, okay, negative 4, okay, over x squared plus 1/2. And all we have to do to find the slope of the tangent line at 4, 3 is just plug in 4 into x. So we're going to have something like that. D over dx equals to negative 4 over 16 plus 1/2. Now negative 4 over 16 is minus 1/4, and 1/2 minus 1/4 is just 1/4. So that's going to be our slope for the tangent line. Okay? So how do we write the equation of the tangent line? Well, we have to put it in point slope form. So we do y minus 3 equals to 1/4 times x minus 4. Now that's going to be the equation of the tangent line. I'm not sure if they're going to ask you to expand the equation, but you could just leave it like that. That's still an equivalent form. Now for part B, we're going to find the tangent line. So now this is the normal to the tangent line. What we have to do is just find the negative reciprocal of the derivative. So negative 1 over dy over dx will be negative 1 over 1/4, which is just negative 4. So we just write the equation. That's going to be y minus 3 equals to negative 4 times x minus 4. Okay, so that's part B. Now for part C, we're just going to find all points where the derivative is 0. So we just set the derivative equal to 0. So that's minus 4 over x squared plus 1/2 equal to 0. Now over here, what we could do is find the common denominator. So we're going to have negative 8 plus x squared. All of that divided by 2x squared. This cancels out if we multiply it on both sides. And when we have that x equals plus or minus root 8, which is just plus or minus root 2 over 2, 2 root 2. So if we have plus or minus 2 root 2, we have 2 points, 2 possible points where the derivative is equal to 0. So we just plug it back into the original function, f of x, to find the y values. So let's plug in root 2 root 2, and let's see what happens. 4 over 2 root 2 plus 2 root 2 over 2. And then what we could do here is find the common denominator. So multiply by root 2 on top and bottom. This over here cancels out, and you're just left with 2 times 2 is 4. 4 plus 4 is 8, so we have 8 over 2 root 2. 8 over 2 is 4, so you have 4 over root 2. And if you rationalize, you're going to get 4 root 2 over 2, which is just 2 root 2. So the first point will be 2 root 2, comma 2 root 2. Quite a repetitive result, but it's interesting. Now we're going to find the y value of negative 2 root 2. So essentially it's the same thing. It's just that you switch the negatives, right? So you just change the sign, and what you're going to get, okay, is negative 2 root 2. So the point will be minus 2 root 2 minus 2 root 2. So the derivative is equal to 0 at these 2 points. Now for question 2, let a body move along the s-axis with its position given as s of t. So we have s of t equals to t cubed minus 6t squared plus 9t, where s of t is measured in meters and of course t in time, in seconds. So for part A, okay, we're going to find the velocity and the acceleration. So we're going to find the acceleration and the velocity functions. For part B, we're going to find when the acceleration is equal to 0. All right, so that means the, oh no, I'm sorry, we're going to find the acceleration, right, when the velocity is equal to 0. And for part C, we're going to find the speed, very different from the velocity, when A is equal to 0, when the acceleration is equal to 0. Now, for this problem, well, it's pretty straightforward. We know that the first time derivative of the position function is the velocity, and the first time derivative of the velocity function is the acceleration function. So we can go ahead and find the velocity. So d over dt of the position function is equal to the velocity function, which is equal to 3t squared minus 12t plus 9. Right? So that's going to be the velocity function. And then the acceleration function is the derivative of the velocity, right? So a of t is equal to d over dt of b of t, which is just 6t minus 12. So those are your acceleration and your velocity functions right there. All right, for part B, we're going to find when the acceleration, okay, the acceleration when v is equal to 0. So what we have to do, we have to find the times at which the velocity is 0. So set v of t equal to 0 and then plug that time into the acceleration to find the value. So right here we have, okay, for part, this is A, this is B. We're going to have 3t squared minus 12t plus 9, and we're going to set it equal to 0. So we're going to find the times at which the velocity is equal to 0. Here we just divide by 3. We have t squared minus 4t plus 3 equal to 0. T minus 3 and t minus 1. So the velocity is 0 at t equals 3 and 1 second. All right, so now we're going to find the value of the acceleration. So we're going to find a of 3 and we're going to find a of 1. Now a of 3 is just going to be 6 times 3, 18, minus 12 is 6. That's 6 meters per second squared. And a of 1, okay, it's just going to be 6 times 1 minus 12 is negative 6. So it's minus 6 meters per second squared. Don't forget the units. If you forget the units, you're going to get a lot of points off. All right, so that's it for part B. Now for part C, the speed when the acceleration is equal to 0. So we do the same process. We want to find the time at which the acceleration is 0. So we just set a of t equal to 0. So 6t minus 12 equals to 0. So t equals 2 seconds. And we plug it back into our velocity function. But in this case, the speed, the definition of the speed is equal to the magnitude of the velocity function, or the absolute value of it, which is just the absolute value of 3t squared minus 12t plus 9. So we just find okay, the speed when the acceleration is equal to 0. But to do that, okay, we have to plug in our time that we found. So we have that the speed is equal to absolute value of 2 squared is 4, 4 times 3 is 12, minus 24 plus 9. And we find that that's equal to the absolute value of negative 3, which is equal to 3 meters per second. So that's the speed, okay, when the acceleration is equal to 0. Don't forget the units. The units for the speed is the same as the units for velocity, meters per second. Moving on to question 3.
I have a question.
Yeah.
So, like, for speed, do we always have to put, like, so, like, if it's asking only for velocity, we only put b of t, but, like, if it's asking for speed specifically, we use absolute value.
Yeah.
You must use absolute value. Yeah.
So, like, what if it's up in the opposite? Like, so it was like, if you were,
Give me an example.
So if you're given the acceleration, you need to find the velocity.
If they give you the acceleration, the question was.
If you're given the velocity, you need to find out the position. You know how you do the integral of the absolute value of dt.
Uh-huh.
How would you integrate? No, not how would you integrate it. Like, would you have to do it every single time? Like
To find the speed?
No, to find the position. Like in the same like.
No, you just take the integral of the velocity function.
So like, would you always use the absolute value? That's what I'm saying.
No, because position is different. If you find distance, then yeah, you have to use the absolute value, and you have to find all the distances from the minimum to the zeros, and you have to add up all the distances. You can't forget about the minima and maxima.
So like, but right now in calculus, like what we learned so far, we only use absolute value of VT if it asks for speed specifically.
Right, if it asks for speed, yeah. So the speed is just absolute value of the velocity function, and the distance is just absolute value of the position function, x of t, or s of t, or whatever they define it as.
Speed can't be negative, right?
Right, it's just a scalar. It's a scalar quantity. Velocity is a vector quantity, so it could be either positive or negative. It doesn't matter. Acceleration is also a vector quantity, and so is position.
All right, that makes sense.
Now, moving on to question 3. Now, for question 3, we're going to find the derivatives, dy over dx, of each of the following. Oh boy. So find dy over dx, okay, of a y equals 2e to the negative x plus x e to the 3x. And for b, we're going to have 3x plus 2 tangent to x, so all of that divided by x secant x. That's equal to y. We're going to find the respective derivatives of each function. So for this one, dy over dx, okay, equals to, here we use the chain rule. We take the derivative of the inside first. So the derivative of negative x is negative 1. So that's negative 2 e to the negative x, okay? Here we use both the chain rule and the product rule because we have product of two different functions. So we just take the derivative of x first, that's 1, times the second, so that's e to the 3x, plus the first times the derivative of the second. We have to take, okay, the derivative of the inside first. In this case, the derivative of 3x is 3, so that's times 3 times e to the 3x, okay? The derivative of e is just e, and that's your answer, okay? You don't have to do anything else. I mean, over here, you just bring 3 outside. Now, for part B, we have 3x plus tangent 2x. This is 2x. Over x secant x equals y. So dy over dx. Here we have to use a combination of several things. We have to use quotient rule, product rule, and chain rule together. So for the quotient rule, we take the derivative of the top function times the bottom minus the derivative of the bottom function times the top. All of that divided by the bottom function squared. So that's going to be 3 plus, okay, the derivative of the inside is 2 times the derivative of tangent of 2x, which is just secant squared of 2x. Okay, that's the derivative of the top function, but we have to multiply it by x secant x. So that's x secant x. And then we subtract the opposite. So we have to take the derivative of the bottom. That's product rule over there. So we have secant of x plus x secant x tangent x. That's the derivative of secant of x. That's secant tangent. And all of that multiplied by the top, right? The top function, which is just 3x plus tangent of 2x. All of this is divided by the bottom function squared, x secant of x squared. I'm not sure if you're required to expand this and then simplify it. It's not like, you have to simplify a lot, but I mean, you could kind of cancel out something here. You could cancel out 3x secant x, as you can see. So if you want to do that, you're going to get something like this. dy over dx equals to 3x secant x, right? And then we're going to have plus 2 secant of x, secant squared 2x, minus, okay, over here we have 3x, right? Again, 3x secant x. And then we have plus, well, all of this is being subtracted, so minus secant of x times tangent of 2x, so that's secant x tan 2x minus x squared, right? 3x squared, because x times 3x is 3x squared, times secant tangent, okay? That's very tedious, as you can see. multiply by that. So, and then finally we have minus x secant of x tangent of x tangent of 2x. See, it's very tedious, so I don't know if you are going to be required to simplify these expressions when you take derivatives. And over here, you cancel out this 3x secant x. All right, so those are going to be the derivatives. Let's go to question 4. We're halfway there. Now for question 4, we're going to find the derivatives again. Find dy over dx of the respective functions. So for a, we're going to have 3xy plus 7, all of that to the second power. This is implicit differentiation, equals to 6y. And for part b, we're going to have y equals to sine of x to the power of x. Very interesting. Now, for part a, we can use implicit differentiation. So we can go ahead and just differentiate this using the chain rule over here. Take the derivative of the inside, product rule over here. So that's going to be 3y plus 3x times the derivative of y, which is just y prime. Okay? And then we're going to multiply the derivative of the inside times the derivative of the outside, right? So we bring 2 down. So that's times 2 times the original 3xy plus 7. All of that equals to 6y prime, right? Now, our ultimate objective is to bring all the y primes together, factor them out, and just find it on its own, right? So right over here, we could just, distribute this over here. So we're going to have 6xy plus 14, right? All of that multiplied by 3y plus 3xy prime. All of that equal to 6y prime. Now, over here, we're going to have 18xy squared plus 42y. And then we're going to have plus 18x squared y prime and plus 42xy prime equals to 6y prime. And what we can do is bring all the y primes to one side and then just factor them out. So we're going to have something like this. We're going to have 18xy squared plus 42y equals to, okay, we factor out a y prime and then we just subtract these two terms, put them on the outer side. So that's going to be y prime, right? So that's going to be 6y prime. Yeah, this 6y prime. Oh, but we're factoring it out. So just y prime times 6, right? Minus this. So minus 18x squared y minus this, which is 42x. Our last step is to divide by this huge factor. So y prime equals to 18xy squared plus 42y. All of that divided by 6 minus 18x squared y minus 42x. And this is your final answer. I don't think you can simplify this any further. Part B, we have y equals sine of x to the x, right? Now in this case, we can either go straight and differentiate this explicitly, but that's just a pain in the ass. So you don't want to do that. You want to take, you're gonna use advantage of the logarithmic rules for differentiation. So if you have y equals sine of x to the power of x, you just take ln of both sides because you have a x power. You want to get rid of that. So ln of y equals to ln of sine of x to the power of x. And according to the logarithmic power rule, we just bring x to this side. So we have ln of y equals x ln of sine x. Okay, and then we want to implicitly differentiate this expression. So the derivative of this side is going to be, in terms of y, 1 over y times y prime equals to, here we use both chain rule and product rule. So derivative of the first is going to be 1 times the second, ln of sine x. And then plus x times the derivative of the second. Here we have to use the chain rule, so that's going to be x cosine of x divided by sine x. And cosine of x over sine x is cotangent of x. So our final answer will be something like ln of sine of x plus x cotangent of x. And then multiplied, right? We have to bring this y to the other side, multiplied by y. But the answer should always be in terms of one variable, always be in terms of x. So what we do is we simply bring y in terms of x. So what is y in terms of x? That's just going to be sine of x to the x, so that's the answer. This is y prime. Now moving on to question 5. Now for question 5 you have to be very careful. Question 5 is about inverse functions. So show all work in obtaining the answers to each of the following. Now for part A, we have suppose that the function y equals f of x is differentiable in an interval containing x equals 3. So we have y equals f of x. We know it's differentiable and it contains x equals 3. Okay, if it's differentiable, we know it's continuous. So that's good to know. And we're also told this piece of information. We're told that f of 3 equals to 8. And that f prime of 3 equals to 2/5. Okay? So that the function has a differentiable inverse, okay, in an interval containing y equals 8. So the function has a differentiable inverse, right, at y equals 8. Here, this is a very tricky part of this question. When they say y equals 8, they don't necessarily say x equals 8. So what we need to do, we need to take advantage, okay, of the fact that when you plug in, okay, when you use the composition of functions for inverse functions, all right, you're going to have symmetry. And that symmetry will be, okay, in x. So when we have a curve like this, suppose you have x squared, we know that the inverse is the square root of x, right? The symmetry lies at y equals x. So, all right, that's what it means. And what happens is that when you plug in, right, one function over into the other. So, but first let me just define the inverse function of x as g of x for simplicity. Now, f of g of x, okay, will be equal to x, right, because of its symmetry. So, but we want to find in this problem the derivative of the inverse function. So we want to find the derivative of this, which is just g prime of x. What's g prime of x? At y equals 8. Okay, at y equals 8. All right, so that's the thing. Now over here, first of all, what I would recommend doing is take the derivative of this to find what is g prime of x in terms of f. So we use the chain rule, so that's going to be g prime of x, right, times the derivative of the outside, so that's going to be f prime of g of x. All of that equals to the derivative of x, which is just 1. So g prime of x is just 1 over f prime of g of x. Okay? And right over here we can say a few things about what the information is given. So we can say that because f of 3 is equal to 8, so once we find that f of, okay, we're given that f of 3 is equal to 8, right? We know that if we take the inverse on both sides, so inverse of this, we're going to cancel out this, so we have 3 equals f inverse of 8, which says that g of 8 is equal to 3, okay? So we can use that in order to find g prime at y equals 8, which in fact means that, okay, x equals 3, okay, really, because at 8, we know that g of 8 is 3. So at x equals 8, okay, g of 8 is equal to 3. So we can use that fact. So basically, what we want to do is we want to find g prime, okay, of 8. So that's 1 over f prime of g of 8. Okay. Now g of 8 is 3. So that's 1 over f prime of 3. And f prime of 3 is just 2/5. So that's 1 over 2/5. And that's 5 over 2. So that's going to be the derivative of the inverse. Question 6. So for part A, we have y equals cotangent inverse of 1 plus 3t. All of that to the power of 1/2. And then we have, okay, part B equals to ln of, okay, sine of, okay, we have ln of sine of theta, cosine of theta, this to the power of 1/2, and then divided by 1 plus 2 ln of theta. Okay, all of that is inside of the logarithm. So to find the derivative of cotangent inverse, well, we can take advantage of the fact that, okay, the cotangent inverse is basically negative tangent inverse, right? So we could say that this is equal to negative, okay, tangent inverse of 1 plus 3t to the power 1/2. So we know that the derivative of tangent inverse is 1 over 1 plus x squared, so dy over dx. It's just going to be the derivative of the inside. That's going to be 3, okay, negative 3, multiplied by, okay, the derivative of the outside here. So that's going to be 1/2 times 1 plus 3t to the power of negative 1/2. And we have to take the derivative of the outside again, so it's double chain rule, so that's 1 plus the inside squared. And 1/2 squared is just 1, so what we're going to have is dy over dx is equal to negative 3, okay, all of that divided by 2 times, what's 1 plus 1, that's 2, so that's 2 plus, okay, plus 3t multiplied by 1 plus 3t to the power 1/2. Okay, so that should be the derivative in its simplest form. Now for b, we have ln of sine theta to the power of 1/2, sine theta cosine theta to the 1/2 over 1 plus 2 ln of theta. Now in this case, we have to take advantage of two things. We have to look at the trig identity that's in here, and we also want to take advantage of the difference of logarithms, right? You know that when you have ln of something over something, that's basically ln of that minus that other thing. So we're going to have something like this: ln of sine theta. Okay, so y equals ln of sine theta cosine theta to the power of 1/2 minus ln of 1 plus 2 ln of theta. Okay. Now in this case, we know that 2 sine of theta cosine theta equals to sine of 2 theta. Okay? So to find cosine theta sine theta, we just divide by 2 on both sides, and we know that sine of 2 theta over 2 equals cosine theta sine theta. So we can substitute this into our logarithm to make things a little bit easier. So we have y equals to ln of sine of 2 theta to the power of 1/2, and of course, thanks to the power rule for logarithms, we can bring the 1/2 outside, so that's 1/2 in the front, and then we have minus ln of 1 plus 2 ln of theta. Now, right over here, it makes a lot more. It makes it easier. Now we're going to take the derivative of this. We use the chain rule only once, right? So that's dy over dx equals to the derivative of the inside is 2, okay, cosine 2 theta. All of that divided by 2 times sine theta. Okay, the derivative of ln of sine 2 theta is 1 over sine 2 theta minus 2, okay, 2 over theta, right? And all of that divided by, okay, 1 plus 2 ln of theta. Very nice. So cosine 2 theta over sine theta is basically cotangent 2 theta. These 2's cancel out, so we have dy over dx equals to cotangent of 2 theta minus 2 over theta plus 2 theta ln theta. And that's going to be the derivative for that function. Right. Question 7. So for question 7, this is a related rates problem. We have a 13-foot ladder on a wall. So we have a wall over here, okay, and there's a ladder leading down the wall, and it's 13 feet long. Now we're told that, okay, this ladder is okay against the vertical wall, and the base is sliding down along the horizontal floor. So basically, this is going this way, right? When base is 5 feet, so this is the base over here. When this is 5 feet, the wall, I mean the ladder over here is going to be moving at 2 feet per second in the x direction. So that's going to be the rate in the x direction, positive x direction, along the floor, right? So how fast is the ladder sliding down the wall at this instant? At the instant when the base is 5 feet. So we're looking for the rate that goes down. So how fast is sliding down in the y direction? Now, we can say the following things. We can assign a few variables for this. So suppose this is a right triangle over here, right? So let's call this distance x, and let's call this distance y, right, from here to here. So we know that according to the Pythagorean theorem, x squared plus y squared equals to 13 squared, which is 169. All right, so that's a good piece of information. Now, because this is the rate in the positive x direction, right, we can say that this is equal to dx over dt. So that's the first time derivative in the x direction. And we want to find, of course, dy over dt. What's that? And of course, we can say that it's negative because it's going downwards. So we choose our the right directions to be positive, the up and right direction to be positive, and the down and left direction to be negative. Now over here, what we could do, okay, is we could implicitly differentiate this. So we can say that 2x dx over dt plus 2y dy over dt equals to 0, right? The derivative of a constant is 0. And look at that. The 2's cancel out, right? And we're left with this. We're looking for dy over dt. So the first time derivative of y, that's going downwards. We know for sure it's going to be negative. So dy over dt equals to, okay, we subtract this, so negative x dx over dt divided by y. We know our x at this instant. We know our dy dx dt. That's 2 feet per second. Do we know y? Well, not really, but we could find it, okay, using the equation that we made over here. So if we solve for y is equal to, okay, the square root of 169 minus x squared. And what is x at this instant that we're trying to find dy over dt? Okay, so x is going to be 5, so y is equal to the square root of 169 minus 5 squared, which is just 25. And 169 minus 25 is 144, so the square root of 144 is 12. So y is 12 at this instant. Now, we just plug in our values. So we have negative 5, right? Negative 5 feet multiplied by dx over dt, which is 2 feet per second. All of that divided by y, which is 12 feet. Okay? Now, the answer to this is going to be, okay, the following. So 5 times 2 is 10, right? So that's 10 over 12. Negative 10 over 12. And we can simplify this a little bit. So we have 5, right? We have 5 and 6. So that's going to be negative 5 over 6 feet per second. And as expected, the answer is negative, which means that it's moving in the downward direction. And sand is being poured onto a conical pile at the rate of 3 cubic meters per second. Right? So we have a cone like this. Okay. And then we have a little hole on the top, and there is sand that's coming in at the rate of 3 meters cubed per second, right? And that is a measure of volume per time. So that's basically dV over dt, the first time derivative of the volume. So that's the rate at which the volume is changing. Now, the sand pile is a right circular cone, we know that, with a circular base on the ground of height h, so the height is h. And the diameter is 2r. So all of this is 2r, which means that the radius is r. And then the height, we're told that the height is equal to 2 times the diameter, 2 times 2r, which is just 4r, okay? So that's good to know. And so we're asked, at what rate is the height increasing when the pile is 6 meters high? So at the instant, okay, at the instant when h equals 6 meters, we want to find, okay, what is the rate? Okay, so what is the rate at which the height is increasing? So what is the h over dt at that instant? Now, we don't know what the radius is, but we could surely use the volume for a cone. The volume for a cone is given, so that's going to be pi r squared times height divided by 3. Okay, so we know that the radius is constant at the instant when the height is 6 feet. So at this point, the radius is a constant, so that's not changing. We know that height for sure will be changing at this time because the volume is increasing, right? So the height has to increase, but the radius is constant at this instant. Now, if we take the first time derivative of the volume, we find dV over dt equals to, okay, pi r squared times the derivative of h, which is just dh over dt, all of that over 3. Now, we know dV over dt, we know r, right? We can find r in terms of in terms of h, and we know our height at that instant where we want to find the rate of change of the height. So we can say that the radius is equal to h over 4, which is equal to 6 over 4 at that instant. So it's 3/2 meters. So we just solve for dh over dt over here to find the rate of change of the height. So dh over dt equals to dv over dt, okay, multiplied by 3 and divided by pi r squared. Now we just substitute our values. We know our radius. We know the rate of change of the volume is 3 meters cubed per second. And so we have something like this: 3 times 3 divided by pi times the radius squared, which is just 3/2 squared. All right, so we have 9 on the top, so that's going to be 9. And then 3 squared is 9. So that 9 and that 9 cancels out, divided by 4. The 4 goes out, and we have that the rate of change of the height with respect to time is going to be 4 over 5 meters per second. All right, so that concludes this review for calculus 1, or math 111, and for the common exam number 2. Thanks for watching. I hope you found this video useful, and remember to subscribe. Check out my Patreon page at patreon.com/marriedmaths, and share with your friends so that it's also useful for somebody else. Good luck on your exams. Have a good day.